Okay, everyone, I try to show my presentation about CNN. First of all, this is the content. On the chapter 1, I will introduce about CNN, what is it, and how to use it, and some feature of it. And the image convolution or filters operation are widely used in various occasions, such as various filters, calculational neural networks, convolution neural networks. Is that chapter 2? I will explain the some example about filtering, like mean filtering and uh, Gaussian filtering. Chapter 3, I will talking about sharpen. Sharpen is also a filter. Chapter 4, we will talking about the differential operator, including first order differential operator and second order differential operator. And at the end, it's a conclusion and reference. First, we look at this image. This image is a good illustration of the basic principles of image convolution. And we also need to know some features about convolution. First of all, the main purpose of the convolution operation is to reduce the dimensionality and vector extension of the image. Second, the convolution kernel is often a matrix with an odd number of rows and columns, so the center is better to position. 3. The sum of the convolution kernel elements reflects the brightness of the output. If the sum of the elements is 1, the brightness of the convolution image is basically the same as that the original image. If the sum of the element is 0, the convolved image is basically black, and the brighter one is that part is often experience a certain feature of the image. That's an important part. We will talking about it later. And then the fourth we are is high pass filter. High pass filter means that only the high frequencies part of the image that is particularly with shape change in the pictures is allowed to pass through, and is often used to sharpen the image and enhance the edge of the object in the image, such as Sobel operator, Previtt operator, sharpening filter, and so on. Number 5 is low pass filter. We can call it LPF, means that only the low frequency part of the image, that is the part that changes slowly in the picture, is allowed to pass through, and is often used blur or smooth the image, remove noise, and so on, such as Gaussian filter and mean filters, and so on. That's the chapter 1 introduction, and then we are talking about mean and Gaussian filters. The mainly we need to know is that the sum of the elements in the filter is 1, and the output brightness is basically the same as the input. Both are low-pass filters mainly used for image rolling, smoothing, processing, and noise remove. The larger the corner and the greater the blur. That's mean and Gaussian filters. It's a very easy, really simple filters. So next one is about sharpening. Sharpening, look at this. two pictures. There's two pictures is we use different sharpening corner to convolute. Later, I will show my code and the result is all about this picture. Then let me explain what is it. The sharpening, the main function of the sharpening convolution kernel is to sharpen the image. That is to make the edge of the image sharper, and the sharpening convolution kernel is also a kind of high-pass filter, just like we are talking about just now. And the convolution kernel calculates the difference between the central pixels and the surrounding pixels. The larger the difference, the greater the change around the element. The greater the frequencies. And the greater the output value, therefore, it's a type of high frequency filter. If the sum of the sharpening convolution kernel elements is 0, it has the effect of extracting image edge information. That's why the left picture is the sum of element is 1. The right picture sum of the element is 0. So the difference of them is that one have colors, one just used to edge detection. That's sharpening. And next, we are talking about some differential operation. First of all is first order differential operator. The first order differential operator can calculate the edge of an object in a certain direction, but it is often sensitive to noise, and the sensitivity of edge detection depends on the size of the object. So we get two examples about first order differential operator. First is private. The private operator is to differential the image to approximate the first derivative of a certain part of the image, since the derivative also has directionality. There are 8 different types of private operators of the same size. The purpose is to find gradients in 8 directions of up, down, left, right, upper left, lower left, upper right, and lower right, like that. And the second is about symbol operation. The symbol operator is an improved version of the private operator, which properly weights the elements in the middle. Now, that's the difference. And the picture shows the result of a Sobel operator's convolution. Next is the second order differential. According to the position of the zero across point of the second derivative of the image, the most dramatic change in the image can be predicted, which may correspond to the edge of the object. Different from the first order differential operators, the second order differential operators have rotation invariance to edge calculation. That's it. Edge is all directions can be detected. So for example, the Laplace operator can approximate the second derivative of the image and has rotation invariance and is that can detect x in all directions. There are 2 types of the Laplace operator which consider the second order differential of adjacency, and adjacency respectively. The first one I show you is the both adjacency detector kernels to convolution, and the result is like this picture. And that's the reference, and I will show my result to you. Yes, that's my program. In this program, we import two software package, and then this sentence show that the picture CV2 image read will read a picture. The picture elements is one means that we read a color image, and the second one, the element is 0 means that we read a gray picture. Now we are setting the kernels. First one is horizontal kernels, 000, 111, and 000. That's the horizontal kernel. And the second one is vertical kernel. And then the third is edge kernel. We have also different sharpened kernels. The first one kernel is for 9, and the sum of the elements is 1. And the second sharpened kernel, the sum of the elements is 0. So that's the difference. We can see the result later. And the last two is Schauber kernels and Laplace kernel, right? And then we use this kernel to put it to calculation with the input image. That's the input image. The parameter of -1 means that the input and output is the same size of the picture. It means we need to padding it. And in this part, we will show the result to Windows, show the pictures, different pictures that's original, grayscale. The two picture of that is also input and horizon convolution, virtual convolution, edge convolution, different sharpen convolution, Schauber convolution, and Laplace. And all of this result we will waiting for your input. If you input anything, we will destroy all of the window and end of the running program. That's the result, and let's start to run it. And okay, we can share this one, and we can see that's the Laplace, and that's horizontal. There's the gravely input. There's the sharpen calculation and different sharpen convolution. First one is the sum of the element is 1, and the second sum of elements is 0. That's the difference with them, and that's an edge convolute, and this the sample, and it's vertical. That's the original picture. That's the difference of them. And we enter any things, any keys, it will close the window and end of the program. That's all. That's all about my sharing. Thank you.